Yeah. Okay, good morning to everybody. We're going to start. Okay, good morning and welcome to the IAA seminar program. And today, I am sure this morning all of you have seen a new press release, yes, showing the analysis of the observations performed with the Event Horizon Telescope in the year 2018. It's the second year that we have an EHT campaign. In fact, this is important because you remember the first images of the black holes in M87 and also in Sagittarius A star. But the fact that we are having already a second epoch observations and second epoch images also is that it permits us just to perform a comparison of the results of 2017 and 2018, and in fact check the predictions from general relativity, which is really fantastic. The presentation today will be given by the EHT group of the Instituto de Astrofísica Andalucía. You know that the EHT is an international collaboration with a large number of institutions from many different countries. But I want to mention that the participation of the group here in the IAA, led by José Luis Gómez, that is here, has been really very relevant. I would say that has been fundamental in the results that have been presented in this paper that has been published today. In fact, you will notice that easily during the talk. Let me, in fact, congratulate the team, congratulate José Luis as leader of the team, congratulate all the team, all my colleagues because of the results they have obtained. That they are fantastic. And I am sure you will enjoy the meeting. I have to excuse myself because I'm taking part just now in the meeting of the Comisión Nacional de Astronomía. I just skipped the meeting for 5 minutes and I have to come back now. But you are in the best hands and I am sure you're going to enjoy the presentation. Then, José Luis, the floor is yours.
Thank you very much, Anton, and thank you very much for taking the time to go out and join us. Okay, so it is really a pleasure to be with you here, and we are having, okay, let me see. Okay, got it. Okay, so as Anton mentioned, we are very proud to have the second epoch observations of the black hole at M87, and I like to just start the presentation by introducing the EHT group at the Instituto de Astrofísica Andalucía, and then they are going to do the actual presentation, and we are going to have contributions from people from Los Angeles and from Korea and Seoul. So the group is formed currently by myself, as I'm also the vice chair of the Science Council of the Event Horizon Telescope, Clotaro Moriyama, who is one of the coordinators of the Imaging Working Group, Falia Traianu, who is now the European Outreach Coordinator for the Event Horizon Telescope. She has been particularly busy today and the past days, as you may imagine. Antonio Fuentes, you all know him. He is our movie maker. He was the lead of the first attempt to get movies of Sajay that we published in 2022. And now we have also new members, starting from Mariana Foski, that he is also contributing to the movie making of the EHT. We will hear a little bit more at the end of the presentation about the next projects of the EHT and the first attempt to get movies of black holes. And then we have Rohan Dahale. Rohan has been also instrumental for the first imaging using a new technique called cone ray. Actually, I'm very, very happy and very proud to say that there is as you have seen, several press releases in different countries, and we have a general press release for the Event Horizon Telescope. You can check this press release in the Event Horizon Telescope webpage, and Rohan Dahale has been highlighted in that press release thanks to his contribution, Rohan and 3 more people. So we are really very proud of the work that Rohan has done for these results. And of course, we have Teresa Toscano, you all know her. She has been also helping a lot with the imaging for these next observations. And Anton Alberti, that you know, and he is, besides being the IAA director, he's also a member of the ambush panels of the EHT. So I'm trying to...
Is it on?
No.
Just open on the slide.
I'm afraid it does not.
With mouse, clicking that.
Okay, Let's use the mouse. Okay, then we have also a new PhD student, Eileen Shen. She's going to join us very soon. She's now in her own country, in China, and she's coming in the next weeks. And she is just joining the EHT. But I want to make a special mention to the former members of the group. Those are Ilya Cho. He's back in Korea, in KASI. And actually, he is going to talk from KASI today and to show us some of the results and some that we have obtained from the EHT. Wang Yao Zhao, who is now at Max Planck Institute for Radio Astronomy in Bonn, and Rocco Lico, who is now at Bologna. So, and with this, I pass this to, I think, Teresa, you are next. Kotaro. Oh, no, actually, yes, I have also this extra slide. Oh, my God. All right, so here I wanted to highlight a little bit each one of the different contributions. You will see this also through all the presentation, and Rohan in particular is going to highlight this. But I want to highlight these 6 people. They are really fundamental, instrumental for this observation. I think we have to be extremely proud of the work of the EHT. We are now one of the most relevant groups in the whole EHT. In Europe, we're one of the 3 largest and most relevant. And as you will see later, we have used many different techniques for getting the images of black holes. And I'm very proud to say that out of the 5 imaging techniques we have used in the house, we have been leading or instrumental in 4 of those techniques. So these images really were made here in the house, as we did for SciJ and M87. And in particular, Rohan led the imaging analysis of the new variation method called Conrad. Ilya Cho was also the lead of the imaging for DIFMAP and EHT imaging. Mariana Fosky and Teresa Toscano has been also contributed significantly to EHT. Salia Traianu, who also collect the comparison with the 2017 data, and Kotaro Moriyama, who joined our group 3 months ago. He has been leading and on the generation of the synthetic data set that we have used to validate the simulations, and also was the leader of the Smiley team. So with this, I pass it to Kotaro, who is going to give us an introduction of the results. There you go, Kotaro. I think you will have to use the method.
Thank you so much for the introduction, Jose. So today, I and Ilja Cho, who is the next speaker, talk about the 2017 M87 milestone, and then based on the this kind of background, we would like to demonstrate the 2018 M87 result. First, let's focus on the 2017 EHT observation. So EHT collaboration is involving over 18 institutions and 300 researchers globally, and focusing on the science and observation in the vicinity of the black hole. As listed here, the EHT observation utilizes the 8 worldwide telescopes at the 6 different locations and constructs a virtual Earth-scale telescope as shown in the right figure. So this is the main motivation for EHT, and our objective is to detect a compact feature like a black hole shadow, as I demonstrate here. So general relativity predicts the strong gravitational field bends the radiation from the surrounding plasma and forming the black hole shadow. So left panel demonstrates the radiation from the surrounding plasma and categorized with 2 important components, cyan and black rays. Here, cyan rays are bended around the black hole due to the strong gravitational field, and then reaches to the distant observer at the right-hand side. But for black rays cannot arrive to the distant observer because which was captured by the event horizon at the center of the black hole. So this contrast between cyan and black rays provides a black hole shadow, as we can see in the 2017 observation. EHT has 2 important targets for black hole shadow detection. First one is the M87 at the nearby radio galaxy and Sagittarius star at our galactic center. And if we perform the numerical simulation and investigate the corresponding size of the black hole shadow, as we can see in the right panel, the corresponding diameter is larger than that of the EHT, shown in the cyan bars. And based on the EHT observation with this resolution, we expected to have this kind of bluer feature due to the EHT nominal resolution. Let's move on to the more detail of the structure of the photon ring morphology. So the rays around the black hole carries a different information depending on the number of the times rotating around the black hole. So first, we would like to focus on the right-hand side movie and demonstrate the detail. So if we focus on the radiation less than half rotation, it provides a nearby plasma information and strong gravitational lensing effect, as shown in this movie. So it is not only for the ring structure, but also the spiral feature of the accretion flow. But if we focus on the photon component, more than half rotation, we can start to see the black hole spacetime information. If we focus on the corresponding figure, we can see the thin ring-like feature, which strongly depends on the black hole spacetime. We can also see this kind of thin ring-like morphology with more than one rotation photon ring component, but it is a little dimmer than that of the N1 component. So in this way, our next target is to detect the N1 component to check the black hole spacetime information. EHT currently observes the all combined photon ring component from n equals 0 to n equals 2, 3, or 5, and we can get this kind of beautiful movie with EHT observation. So the decomposition of the photon ring morphology can be addressed with the future EHT, and which will be demonstrated at the end of this seminar. So black hole spacetime itself is uniquely described with the black hole mass and black hole spin, which is a rotation magnitude of the spin black hole. And if we introduce the black hole spin, the corresponding photon black hole shadow is quite different each other. So if we focus on the non-spinning black hole, as shown in the left panel, the corresponding black hole shadow is symmetric from top to bottom side. But if we introduce the spinning black hole, the corresponding radiation provides a frame tracking effect around the black hole, and this provides a counterclockwise black hole, and the corresponding radiation is strongly bended around the event horizon. And it provides a little smaller black hole shadow size and asymmetric morphology of the black hole shadow. And based on this kind of effect, including our viewing angle, the plus minus 4% size difference between the black hole spin and the viewing angle. So based on this kind of theoretical background, we would like to first demonstrate the 2017 M87 result. We had three important milestones. So first one is, of course, we obtained the horizon scale image morphology of M87 and Sagittarius, and which provides a quite beautiful black hole ring structure, which is consistent with general relativity. And importantly speaking, the Sagittarius and M87 mass ranging from millions to billions solar mass. So these kind of multiple observation enable us to perform the general relativity test among various large scale of the black hole mass scale. And the second thing is we also perform the quasi-simultaneous multi-frequency observation and demonstrated that the black hole powers active galactic nuclei. It is also important for the astrophysical problem. And as described in the next speaker, Ilje Cho, we also perform the polarization horizon scale image and obtain the accurate measurement of the accretion flow property and the background magnetic field structure. So let's move on to the 2017 M87 non-polarization image result. So as a detailed thing, we have four important points. First, we obtain the 42 microsecond ring diameter, which is consistent with the general relativity prediction. And the second thing is it is a strong constraint of the black hole mass. So the size of the diameter is mainly dependent on the black hole mass and distance from the Earth. So based on this morphology, we constrain the M87 black hole mass. And the third thing is the ring stability. As shown in the left panel, from April 5th to April 11th, we obtained a quite similar ring homology in 2017. It is strongly consistent with the general relativity prediction because black hole mass does not significantly change with the supermassive black hole. And also, this asymmetry provides the information of the black hole rotation. For instance, if we focus on the clockwise and counterclockwise black hole case, the corresponding simulation is shown in the right panel. And if we focus on the clockwise black hole rotation, the brightness region located at the bottom component, but counterclockwise black hole predicts the upper brightness component. So based on the consistency between theory and observation, we start to see the black hole rotation morphology for M87. And finally, I would like to quickly recap the multi-frequency observation. So in addition to the 2017 EHT observation, simultaneous multi-frequency observation was performed and obtained the various kind of jet to photon ring morphology based on the VLBI observations. So this result demonstrates the black hole such as the M87 powers active galactic nuclei. So this is also important for the astrophysics. And more exciting news for linear polarization will be provided by next speaker, Ilse Cho. So I would like to pass the speaker to Ilse Cho. Okay. Yep. Ilse, is it okay for you?
Sure. So you're gonna share the same screen, right?
Oh, yep. I would like to move on to your slide.
Okay. Yeah. Thanks, Kotaro. Yes, I'm Ilse Cho at Kashi and Yonsei University in Korea, and I was in IASC until last October, so it is really glad to meet everyone here. Anyway, as Kotaro introduced, here I will briefly introduce the EHT polarization results towards the M87. So in 2021, the magnetic field structure at event horizon scale of M87 was revealed for the first time. Here, the figures show the linear polarization pattern, which are kind of the spiral-like, and that's like consistent across 4 different epochs as shown in the middle figures. Next page, please.
Okay.
Yeah, so based on these patterns, we compared the magnetic field structures, and this supports the poloidal magnetic field structure. For instance, if the magnetic fields are the toroidal, which has been shown in the left side of this right figure, then the linear polarization pattern is expected like radial, as shown. So the poloidal magnetic field is kind of the combination of the radial and the vertical components. So that is what we have revealed from the polarization, the results, the structure, and then the fractional polarization was found up to 15%, and the magnetic field strength is in between 1 to 30 Gauss. Next page, please. Yeah, in addition, like these results support the particular type of the accretion flow model named magnetically arrested disk, so-called MED. There are 2 different branches of the accretion flow models. One is MED here, and another one is named SANE. The MED model has the strong and ordered magnetic field, so it is easy to produce the strong jet, while the same model has weak and turbulent the magnetic field. So based on this comparison with the GRMHT simulation models, the observed polarization results from the EHT supports the MED scenario for the M87. Yeah. Okay, so in addition to the linear polarization, in 2023, the results of the circular polarization was also published. Due to the weak nature of the circular polarization, unfortunately, the morphology of the circular polarization pattern is still uncertain across even across the different methods. But it was possible to put some kind of constraints of the upper limit of it. And Still, again, remarkably, from the circular polarization as well, the results supports the MED scenario, which is consistent with the linear polarization results. So these are the brief summary of the polarization, the results towards the M87 so far, and then we can now move on to the next observations.
All right. So thanks for this wonderful background information. So let's now properly introduce the new observations of 2018, as I'm sure you're all excited about. So first of all, you just went through the results of 2017. For the 2018 campaign, we observed in April, from April 18 to April 29th, but the days where we got the data are April 21st, 22nd, 25th, and 28th, with 9 telescopes, which is different, slightly different than the previous observations. Because, first of all, we added 1 telescope, which is vitally important, the Greenland telescope, GLT, which is over there. You can see it in the red circle in the North Pole. Second of all, we doubled the bandwidth of the 2017 observations from 2 to 4 bands, which actually increases the sensitivity and improves it by a factor of √2. And third of all, the telescope LMT improved its sensitivity by increasing its effective diameter from 32.5 meters to its full capacity at 50 meters. Now, especially I would like to emphasize the GLT telescope because of the following. First of all, because it will improve the UV coverage, which for those of you who are not that familiar with this terminology, it's basically we are sampling the spatial frequencies in the Fourier domain, and later on my colleague will explain further on that. And you can see that the GLT baselines with the rest of the telescopes, as signaled in red, those are not just, of course, in the north-south direction, it's fulfilling a lot of the plane, but it's not important just because it's more information, which is great, but also because it's completely new information, since we have never been able to sample that orientation of the map. So that is great. And the thing is that it will be observed in band 3 and 4. So these bands will be key for the image. And I would like to point out that this UV coverage is the best one, and the one that will be used in the image that we'll show later on, which is the April 21st. But I would also like to mention that the second best day is April 25th, but we could not be able to use it because there were some coherent losses and some other problems that will be mentioned later on in the presentation by Mariana. So, did I click? Am I not clicking? Okay, right. So lastly, I would like to also say that these new data was also recorded in dual polarization, which of course will come up in a later paper. And also that, as always, we also have these issues that do not like, but it's normal, which is the bad weather. And in this case, it made it a little bit more complicated to deal with this data. And sometimes we got some signal to noise ratio a bit worse than 2017, but luckily, that's what the GLT made up for. So also the LMT had a late start, which is the reason why you can see in the picture on my left, but you're right, the gray points is the 2017 observations, so you can compare. And there's a difference in the UV coverage, and this is due to this late start and bad weather. But nonetheless, with this new data, we can actually probe better the nulls in the image, which you can see in the visibility amplitude ones, where we can see plotted on a dotted line. This is a Bessel function, which represents the Fourier transform of a perfect ideal ring. And the gray points are the previous observations, and the colorful points are the new ones. So if you check, actually the purple ones, the purple dots are the ones that are probing better this null. So all in all, I just wanted to finish this part of the observations by saying that you're going to see that this is not just another image, but this multi-year observation will actually provide an independent set of a snapshot of information for the black hole, which will allow us to constrain better the intrinsic structure of the variability and accretion flow, and of course, refine those physical tricky parameters of the black hole. So without further ado, I will give entrance to next speaker, Rohan, who will tell us all about how to get there.
Perfect. So now that we already have some kind of introduction of what has been in the past and what it really means with the new observations, I think we should really talk about how to get to the main results. And here I want to quickly mention that what does it mean from going from taking data to actually making the images. And so I think Teresa has already mentioned that what we have is like telescopes all over the world, which form our instrument array. And what we are recording is this interferometric response of these pair of telescopes. And what we do is that once we have this interferometric response collected, which samples the spatial frequencies, as she mentioned, we take all this data and go to a central location and correlate the data. Once we have the data correlated, now we have to deal with some calibration, which can be like in atmospheric effects or the instrumental effects. And only after that, the data is calibrated, we can actually move on to do the imaging. So we actually use two different calibration pipelines to make sure that there's consistency between data. And I think it's important to realize here that, first of all, the data is actually poorly sampled in the Fourier domain. And we are actually pushing the limits of VLBI here. We are observing at 1 millimeter. And that's exactly why I think we should be very careful with what the data we're using. And that's why we are using multiple methods for this. So we actually, when we observe the data, we have both the amplitudes and the phases. Okay, we have this data now. And now we can do two things with it. We can now go to the image domain and make images of it. Or we can just directly fit the data and then figure out our parameters of interest, for example, the diameter. Okay, so I'll first start with speaking about what does it mean to do interferometric imaging. And what that really means is that once we have this sparse measurements in the Fourier domain, which is actually incompletely sampled Fourier transformation of the actual source that we are observing. One important thing I want to realize here with the movie that I just displayed here is that since we actually have this sparse measurements, if we are not careful about what really physically means, we can actually get like whatever we want. For example, a teapot that was just showed here. And so we actually need like robust imaging algorithms, physically motivated and different algorithms to make sure that what we are seeing is actually what we are seeing. And once we have this imaging algorithms, only then we can actually go on to seeing what images that we think. Okay, so I'm going to start with describing different imaging algorithms that we used in this paper. And two of them are a clean imaging algorithm and an RML imaging, which is the regularized maximum likelihood imaging algorithm. So I think many people here might be aware of what is meant by clean imaging, especially the radio astronomers. So in this way, it's like a more inverse approach. We actually have the data in the Fourier domain, and what we do is we just take the Fourier transformation of it and then replace in the image domain by its point source components. Eventually, we also try to solve for the gains at these telescopes. And we do this process iteratively until the image gets better and better and matches the data, describes the data very well. So this has been a more traditional approach that we have used, and it has been used in decades. It's a very robust approach. But since we are actually using data that we are pushing the limits of VLBI here at 1 millimeter, we actually, in 2019 paper, we actually had developed our own algorithms for imaging, and namely EHT and Smiley. And these are like a MEM method, like maximum entropy methods. And this is more like a different approach than the previous one. Here we take more like a forward approach. We start with the initial image, and then we take the Fourier transformation of that. And then we compare that with the actual data that we have. And we try to minimize the difference between the image that we are creating versus the data that we have. And for that, we actually regulate how to get an image by motivated by physics. So for example, we actually regulate this minimization by saying that, okay, the image should be non-negative for sure, and then the image should be smooth where it should be. So by using all this physical information, we can actually reach to the image that would best describe the data. That would be the difference between two of these algorithms. And here, if we just iteratively go towards the minimization, here also we can find an image. This is from the 2017 observations though. Okay, so another approach that we can take by working with this data is like a Bayesian approach. So we actually have some observations taken, and then we want to find a best, we want to find the distribution of models, the probability distribution of models that describe the data. So what we do is we just figure out a likelihood distribution, which is like what is the distribution of the model, distribution of the observations given a particular model. And then we also give some prior information of the parameters of the model. And from there, we can actually sample the distribution of the probability of images given the data. So for that, actually, we performed, first of all, imaging. And for that, we use two different imaging algorithms, Themis and Comrade. So Themis has actually been used in the past. Comrade algorithm was actually used in the Saji papers as well for a different purpose, like modeling. And so we use both of these methods, but we also did something like modeling, as I mentioned before. We can directly fit in the Fourier domain rather than making an image. And for that, we actually used many different models, like a crescent or a ring or a double or disk. And what we found is that actually the ring or crescent models are more preferred for our data. What we can actually do is also do something hybrid. We can fit some geometrical model, and we can fit the background with pixels. And that would be more hybrid approach that was also taken by the Themis algorithm. Okay, so now that we actually have the methods briefly described what they do, I think before applying to the data, what we should really do is validate the methods. Like how well do they really work before we actually do it on the real observations. And for that, what we did is that we went ahead and created lots of different synthetic data of different models that we can have. And by visual inspections, what we see here is that just look at the points in orange, which are the actual data, and the purple points, which are the model. Visually, it looks like it can be anything. I mean, so what is important is that our algorithm should be able to recover the differences and all different synthetic data. So for three of the imaging methods that I mentioned previously, which is the clean imaging, DiffMap, and RML imaging, EHT and Smiley, as you can see here, they very well reconstruct the ground truth here. And I think that it's remarkable how they do this for all different kinds of models. We also saw that the Bayesian approach algorithms, which is the Themis and Comrade, and they also do this quite well. So one important thing to note here is that we are only showing one sample of all the probability distribution of the Bayesian methods here. Okay, so now that we actually created all these images, we checked actually how many images we made. We made close to about 1 million images. Okay, so it's really an impressive, I think, thing that we see here from all the different reconstructions. Okay, so now in the past, I've mentioned that there were parameters that we need for all the clean imaging and RML imaging, but before applying to the data, we should really choose the parameters or select the ones that actually work well for the real data. How do we do that? We actually chose one of these 4 models and chose only those parameters that simultaneously work the best recovering the ground truth. And this is how we chose the parameters. Then we used these parameters and applied on the rest of the data and did a method validation right over there. And for rest of the method with the Bayesian approach, all of them were just like a method validation. And that's how we say that, okay, now the methods are actually working. And I think right after this, we should now jump into, okay, the actual data, because I think that's the next important task. Okay, so just another black hole. I guess by now everyone has seen this, and everyone is wondering, why are these guys making an image of black hole and again, the same source, the same black hole, and how much are they going to keep doing this, and for how long are you guys going to keep doing this? I mean, seriously, I also keep wondering, why are we doing this sometimes? Okay, but the joke aside, I think what is important is that, as Teresa also mentioned while taking the new observations, is that we are continuously improving our array and instrument. And what helps us with that is that when we try to extract our parameters for GR and generativity, we are actually putting better constraints on it. So we are refining our constraints on it by taking more observations. Therefore, that's one of the reasons. But let's put the image of 2017 alongside this 2018 image that we took. What do we see here? So I think one of the most remarkable things here, that as expected, the ring size is the same as that was saw in 2017. And why is this important? I think it's important because, well, M87 has low accretion rate, meaning the matter is going slowly and the mass of M87 is actually it's increasing very slowly over the lifespan of human history. GR, as expected, says that if the mass is the similar or same, the ring size should be the same. And I think it's a living proof that it's actually the same size, and that's how we tested GR. But well, just a funny thing. Let's assume that if it was not of the same size, I think that would be one bigger deal, right? Because we would not have the same size. The GR is not working anymore. Okay, I think that's the Nobel Prize. That's about the ring size. But one other important difference that we see right here is that the brightest spot has moved counterclockwise by about 30 degrees. And I think this important observation is really going to help us refine our theoretical model, especially to better understand black hole accretion. And I think in the next presentations, you'll understand better how we can extract information about this and how can refine our theories from this information. Okay. So the image that I just showed you here was actually an average image of all the different methods of imaging that I had showed you guys before. And I think it's important to, and it's amazing to see here that all the different methods are actually recovering exactly, like more or less exactly the same thing. It's quite consistent with each other. And the other important thing that I want to point out here is that if you see the names in bold, and as also Jose mentioned previously, out of the 5 imaging algorithms, 4 of them were done in-house right here. And I don't want to repeat the names again because they were mentioned quite some time by now. I just wanted to highlight it again. Okay. The other thing that I want to mention is that other than modeling, imaging, we also did modeling, which I mentioned previously. So the best models that we had, if you just blur them to the nominal resolution of the instrument, we actually see the results are quite consistent with the imaging methods as well. And on the top, you can see that they use this image actually average of just the first 5 imaging methods. Okay, we do have the images now. Okay, but yeah, we can't just be happy with pretty pictures, right? We have to do some physics with it. So now that we have the images, I think we should really start extracting the parameters that we want to test our theories. And I think one of them could be like diameter. But I think we should really move on to hearing from Mariana, who is now joining us from Caltech. It's 3 a.m. over there. She's making a lot of effort to join this. And she's going to talk us through how we can really extract the parameters of interest from here. So let's actually, can you turn on your camera, Mariana?
Yes, I should be here.
Okay. Okay. Let's put on your slides. Okay, you can.
Okay. Great, thank you, Ron. So just like Ron was saying, once all the different imaging methods and modeling methods have provided the best fit images and models, the next interesting step is to perform feature extraction. So what do we mean by that? So since it is clear that from all our imaging results, we have a ring-like structure in the images, what we would like to do is to quantitatively characterize the features of this ring. And next, please. Oh. Okay, so in particular, we would like to estimate the diameter, the width, the position angle, which is the point of the maximum brightness along the ring, the brightness asymmetry, and the ratio between the brightness of the ring and the brightness of the shadow at the center of the image. So in this work, we are performing this feature extraction using 2 different methods. Next, please. The first one is called the ring extractor, and it's a method based on the assumption that we already have a ring-like structure in the image, and it quantifies the geometrical features based on definition defined on the discretized image. We also use a second method, which is called variational image domain analysis, which is a Bayesian approach that optimizes the parameters of an analytic model and fits this model to the image. And then the features are extracted as the parameters of the best fitted model. So let's see what are the results that are coming out of these 2 methods. You can see them in the plot on the right, and let me guide you through it because it's a bit chaotic otherwise. So in the first line, we are showing the estimations of the diameter. In the second line, the estimation of the width of the ring. And in the third line, the position angle. The column in gray is showing results for April 21st, while the column in white results for April 25th. So as Teresa was saying earlier, the coverage that we had on April 25th is worse than the coverage than we have on April 21st. And this is why we have a wider standard deviation and a wider uncertainty on the estimation for those values. So let's focus on April 21st. As you can see, the different points are showing the estimations for different bands and different imaging methods and different feature extraction algorithms. And they're all providing very consistent results. The only outlier that we see is in the case of the diffmap imaging pipeline for the estimation of the width. But this is explained by the fact that the width of the ring depends on the effective resolution of the image. And since diffmap is the only method that is not able to achieve super resolution, it will provide a wider width compared to the others. So summing up these results, we have an estimate of the diameter to be around 42 microarc seconds, which is in agreement with the results that we had in 2017. We measure a position angle of 215 degrees, which is instead a clear shift from the 180 degrees that we had in 2017. We measure a brightness asymmetry between 0.2 and 0.4, which indicates that we actually don't have a perfect ring, but we have more of a crescent shape. And we measure a fractional central brightness between 0 and 0.5, indicating that we actually see a shadow at the center of the black hole image. So actually, this is not the only way we can extract features of the ring, but another method, next slide, is by performing direct geometrical modeling. So this is what Ron was mentioning earlier, talking about the modeling pipelines. Because indeed we can have a parameterized analytic function that is describing a crescent or a ring, and optimize the parameters of this function directly in the visibility domain. So not in the image domain, but in the Fourier transform of the image, which is where we have the actual data, and extract the features of this ring as the best fit parameters. So we have two pipelines, which are Themis and Comrade, that perform this kind of analysis. And they can fit different models, so not only ring models, but also Gaussians and disks. And by looking at the posterior distributions of these fits, we see that there is a clear preference for ring-like shapes. So here in the images, you are seeing the three best fit models results. So all these okay. So all the results from the direct modeling are shown in these plots. In the top left, you can see results for the diameter. In the top right, for the width. Center left for the position angle, and so on for all the parameters. Since these results are very much in agreement with the ones I showed before, I will not spend too much time on the plot. But I would like to highlight the fact that the values estimated for 2018, which you can see in blue, red, and orange, are very much in agreement with the ones we measured in 2017, which are shown in black, except for the position angle that is showing a clear shift, and also for the diameter, which is showing a slight increase. But this is due to the fact that with geometric modeling, we can fit very thin ring that correspond to a slightly wider diameter compared to a blurry thick ring. So combining together the different results from different feature extraction methods, different pipelines, we can have an estimate of, next slide, please, of the ring diameter and the position angle. So we have a ring diameter of 43.3 microarc seconds for 2018, which is compatible within the error bars with the estimation of 42 from 2017. And a position angle of 208 degrees, which is a counterclockwise shift compared to the estimation that we had in 2017. So now Talia will explain to us a bit more about the interpretations of these extracted parameters.
Thank you, Mariana. So as Mariana mentioned, explained to us, we measured the diameter, and now we need to interpret it. So for passing from the observational quantities to a physical scale of a black hole, it's very important because is this the step that we need to take in order to test theoretical models and theoretical predictions, for instance, by general relativity. So for this reason, we use the most a common physical scale that describes best massive supermassive black hole, which is the gravitational radius. So the gravitational radius is So the gravitational radius theoretically is defined is a function of the black hole mass, the distance from the Earth, and the gravitational constant, but also can be predicted. General relativity is a metric for general relativity, so can give us a quantity that can reflect different physical processes of the black hole. For instance, the spin of the black hole and the orientation and so on. So theoretically, the value of the gravitational radius is about half of the Schwarzschild radii that Kotaro mentioned earlier. However, because again, as Kotaro nicely explained to us, we are not able to see yet the N2 ring or N1 ring that are described by the general relativity and are connected with the gravitational radius, but we see N0, which N0 is a blending of N2, N1, and the astrophysics that takes place in this region, and also lensing. The light is from these rings is lensed there. So the expected diameter of this of the gravitational radius is increased by a factor of 5 from all these effects. So for the N1 ring, the expected parameter theoretically is about 10.4 Schwarzschild radii. But how can link our observations with theory now? The gravitational radius can also be calculated by the ring diameter that we measure in our images, but with a scaling factor that reflects all these physical processes that I mentioned. Yeah. Now we have measured by the fixture extraction analysis, we have measured the diameter of the ring for our observations, but we need now to determine from the theory the alpha, to do what is so known about as alpha calibration. So for this reason, we generate a library of general relativity GRMHD simulations with different spins, different values of spins, different electron temperature prescriptions, inclinations, and so on. So creating thousands of simulations. The next step is we take these simulations, and based on this, we create for each and every one a UV dataset, a dataset that creates as Teresa mentioned, the array would observe if the black hole was described by these parameters. Then we take each one of these data sets and we image it, as Rohan mentioned, with all the five methods. And next, as Mariana mentioned, we applied all this picture extraction process again to each and every one. And from all this process, we are able to we compare with our observations, and we are able to deconstrain the alpha parameter, which is typical in this range, and we compare it with the data. But so we have so now it's not going to happen. Yeah, perfect. So we have obtained the theoretical alpha parameter. But the photon ring that we see is it agrees, but with the observation. But from the simulations, the observations are slightly larger than the simulations that tell us that we need to expect from a black hole with these parameters. And so we know that we have also a 10% uncertainty of all this process, because many quantities are contribute to this analysis. So for this, again, we need to keep our mind that the ring that we see is a blending of individual rings. So we need higher fidelity images in order to distinguish, for instance, the N1 ring, which is the well-defined by general relativity, and understand its contribution. For this, all this analysis that I showed you was based for the 2017 data. For 2018 data, we are going to do the same. And in order to reconstrain the alpha parameter for this data set. However, because of the consistency, because of the consistent diameter of the ring with 2017 observations that we see there, we can already have a teaser of what we should expect about the gravitational radiation 2018 data. So here you see from the different the consistency for starters of the gravitational radius between its imaging method. The error bars is 86% the confidence interval, and the black squares are the 2017 data. So if we remember, the gravitational radius is also a function of the mass of the black hole. So constraining accurately the gravitational radius gives us the opportunity to also measure the black hole mass. For back to 2017, we used our observations and we calculated the mass based on the gravitational radius, and we compare it with independent mass measurement methods. For instance, here for M87, we have the estimation from, we have the measurement from the stellar dynamics, the motion of the stars around the black hole, the gas dynamics, which is the red line, and our observations, assuming that we are dealing with a supermassive black hole that is rotating. It's a Kerr. It's a type it's Kerr type black hole, and the EHT observations agreed with the stellar dynamics measurement, independent measurement. So this gives us actually practically gives us the confidence that the piece of information that actually M87 is a Kerr black hole, is rotating, has spin. So in the next few months, we are going to have we're going to publish a following up paper with more carefully constrained all these parameters that I told you already. But we know know already that we have a very accurate measurement. Sorry. So, and then we pass to, as Mariana mentioned, we pass to the another difference that we saw with 2017 data, which is the M87 position angle. So here we see a simulation of the plasma, the material around the black hole accreted to the center, and from this simulation we see that the changes in the brightness and the position are matched with the changes that we see in our observations, and these changes are assigned to, as we said, to the astrophysics, to the N1 ring, to the temperature of electrons, and so on. So, but now what we want to do, and we need a higher, we need to be able to see higher order rings, is to distinguish the contribution and quantify as accurately as we can the contribution of its parameter in order to understand better and test further the GR. And we know, I'm sorry, I need to no, okay. But for the large scale jet, we know already that is precessing. We are dealing with a a black hole that is precessing, and this effect will also plays a role for the positional grid, most probably for the positional grid changes that we saw in our data between 2017 and 2018. And now Jose Luis is gonna tell us about the future and yeah, see what is next.
Thank you very much, Cesalia. I think I'm gonna use this. Okay, so this is just the last slide. So first of all, thank you very much for all the presentation. I think this, I hope you got a nice overview of how we do this and our contributions. I'm gonna just finish by commenting some of the future results that you may be expecting from the EHT. As they have been mentioning, Thalia and Rohan and so on, this is the observational paper from the 2018 data. We are just finishing up the theory paper, and we are going to submit this very soon with our new analysis for the theoretical interpretation of the black hole in M87. And we actually just submitted also a paper with the polarization analysis of the psi j of the black hole at the galactic center. I think this is going to be one of the most expected results from the EHT because, as you know, in 2020, the confirmation of the existence of a very compact object at the galactic center was recognized with the Nobel Prize in physics. And so now we are going to tell about what is the actual physics, the magnetic field in the galactic center. And we are one of the most important projects in which the EHT is now embarked is dynamical imaging of black holes. We want to make the first movies of black holes. And I'm very happy to report that our group is leading the effort of the EHT into getting the first movies of black holes, something that was initiated by the pioneering work by Antonio Fuentes here in the house. And we are going to have a workshop in which many of the researchers from the EHT are coming to Granada, and this is going to be at the end of February, and we will discuss all the progress for making movies of black holes, and in particular of psi j. We also want to make time sequence images of M87, and of course, we want also to get the first detection of the M87 together with the EHT data. But this is just in the next few months, in the next year. In the long term, what you have seen is that actually the second observations of the EHT of M87, but we also took observations in 2018, 2021, 2022, 2023, and we are going to take observations in a few weeks from now. And we have been improving the array, so you will see significant improvements in the image fidelity with these new observations. We are also looking for other targets besides M87 and psi j, and we have also just submitted a big proposal to NSF of about 100 million to include the new telescopes in array, and I'm very happy to report that one of those telescopes is going to be in Canary Islands, and this is going to be managed by our institute. And we are also now discussing with NASA, and in a month I'm going also to NASA to discuss a new space media mission. NASA is very eager to send one antenna to the space to do the first space media observations at millimeter wavelengths. And with this, we do expect to get the N1 ring. And as Mariana was mentioning, or Kotaro and Saria was mentioning, N1 is the ring that tells us about the metric. This is the one that actually tells us how black holes actually work. What is the actual metric of the space-time in this object, or whether it's a curved black hole or perhaps it's something else. And N0 is the one that gives us all the astrophysics. It's very important for astrophysics, actually, because this is the one that tells us how black holes actually accrete material and how we can extract energy from these black holes and produce these amazing jets of material. So in the long term, as I mentioned, our final goal for the EHT is to get this ever precise, more refined test of GR. And we do expect to get this in the next year with the next generation Horizon telescope, as well as with the Black Hole Explorer from NASA. So stay tuned. You will see more images of black holes. and hopefully the next splashy results are going to be the first movies of actual black holes that are going to be, brewed and cooked here in the house. Thank you very much for your attention, and we are here very happy to take any questions that you may have.
Do you want to manage the questions?
Sorry?
Do you want to manage?
Yeah, well, but it's up to you. No,
Okay.
You do it, and then we
Questions from the team?
Am I able to make a question?
Sure, please.
Okay, maybe this is a naive question, but where does the light come from, the photons? I mean, what is the physical process that gives rise to the photons that are deviating?
Yes, indeed. This is an excellent question. Do you want to take it, Cortado, or should I?
Yes, but sorry, could you say again?
What is the source of photon? So the
What
heat.
is the source of the photons? Where do the photons come from? What is the physical process that gives rise them?
That's a great question. So thank you so much for the question. So typically speaking, there is a two main origins of the photon radiation. First is the accretion disk in the vicinity of the black hole. So both Sagittarius and the M87 has a radiative thin accretion disk around the black hole, and which is captured by the event horizon. So which is the main candidate for the radiation component. And the second one is, as we shown in the multi-frequency observation, M87 has a quite strong jet component, which is also another main radiation origin for the both black hole shadow and jet component. While Sagittarius is not it is not detected currently as a jet component, but perhaps we may have a little small jet component in the vicinity of the black hole. So answer to your question is both accretion disk and the jet component will provide the main radiation of the photon ring. Okay.
Okay.
There is a question on the chat. Miguel Pérez Torres asked, what is the time scale for the construction and function of the antenna in the Canarias?
I think I can take this one. Thanks a lot, Miguel, for this question. We have submitted the proposal now, and we will know about the proposal more or less in 2025. If the proposal is accepted, we will start building the four new dishes. One, as I mentioned, is going to be in the Canary Islands. Another one is in Chile. Another one is in Mexico. Another one in Wyoming. The first one is going to be in simultaneously in Canary Islands and in Wyoming. So we expect that we will start building the telescope sometime around mid-2025. So and it will take probably 1-2 years or 3 years after completion and commissioning and so on. So we do expect that this is going to happen in the next 4 to 5 years. Okay.
Okay, there is another question by Miguel Pérez Torres.
Okay.
What specific general relativity test are you aiming to address with the current EHT, and which ones cannot be addressed now that you will address?
Yeah, that is an excellent question indeed, Miguel Angel. So with the EHT, what we can do now is we can go up to 345 gigahertz. So we will increase a little bit the angular resolution, and but in order to actually get the very reliable movies of black holes and to be able to observe sources which are significantly dimmer and observe other sources beyond M87 and Psi-J, and start doing some statistical analysis of black holes and black hole demographics and so on. This is the thing that only the NGHT will be able to do. And we think that with the NGHT, also by studying the polarization of the N1 ring, we will be able to actually get very accurate determinations of the spin of black holes. So this, what we are aiming in the future is to get spin determinations to increase the fidelity or to provide to get more accurate tests of GR and to study the black hole demographics. And these are the main scientific goals of the NGHT. And with the Black Hole Explorer, the Space Via mission, and I think this is going to fly more or less at the same time as the NGHT, because NASA is really very eager. We had a meeting in Washington 4 months ago, and we are having another meeting in mid-February in Nashville. NASA is very eager to send this mission. And I think it may be flying in 3-4 years from now. Most of the technology is ready, especially the laser communications, which are needed for the high bandwidth that we are expecting. And with the NGHT, we do expect to see N1, and very clearly to see N1. And with N1, we will definitely determine whether these objects are really described by Kerr, or there is any deviation from the Kerr metric. Yes, please.
In addition to the NGHT, EHT year scale observation may help us to constrain the black hole spacetime. For instance, today we obtain the position angle difference of the photonic morphology, but which also depend on the black hole spin and the black hole spacetime. If we focus on the negative black hole spin, the corresponding variation is so rapid, so fluctuated, and there's quite a stochastic variability among year scale. But if we focus on the positive and large spin scale, the corresponding position angle is almost stable. So if we if we obtain the stable position angle of the M87 ring morphology, we may be able to constrain the black hole spin information, not only for NGHT, which is the strongest evidence based on the N=1, but current continuous EHT is also important to understand the black hole spacetime.
Something that I also like to mention is that if you think about these two objects, SIG and M87, they have been there for millions of years, and they're going to be there for millions of years. So imagine what kind of instruments we are going to have, not just, NGEHT or the Black Hole Explorer. Imagine, X-ray interferometer. Imagine an infrared interferometer, to things like that in 20, 30, 50 years from now. With these objects are going to be there. So we are going to be, these are perfect laboratories for studying GR. So indeed, in 10, 20, 30 years, we will be able to tell whether, there is any deviation from GR in this object, and whether there is any, indication that we can actually get an idea of how quantum mechanics and GR work in these objects. So I think this is just the beginning. As I say, you will see more images of black holes, and of course, many of them are going to look like, another image of the black hole. But this is just the beginning of this long-term quest for studying these objects.
Okay, so the Black Hole Explorer mission, what's the time scale of which you're expecting to descend? The Black Hole Explorer.
Yes. This is NASA is very eager to go for this, and now JAXA, the Japanese Space Agency, is also putting money. They want to do the cryogenics of the telescope. So I think this could fly as soon as in 3-4 years, or even less than that. But the timing is also very good, because you have antennas in space. You also need a good ground array. You need more antennas on the ground. So I think the timing is going to be very good for having more antennas on the ground with the NGEHT, and then the antenna on space. And this is going to be really, I think, definitely this is going to be a killer result, because for the first time we will actually see what happens really at the strongest gravitational curvature of the space-time that you could imagine, which is one of these black holes.
So we have a question in the room, and then another one in Zoom. Yes,
question for
yeah.
So you talk about, so I know cleaning, right?
Yeah.
You talk about the difference between clean and other ways to kind of model these data, right? And then you talk about
Comrade, yeah.
and many different things. So these are like clean or they're different?
No, they are not clean. Okay, I guess I wasn't clear.
No,
So clean is when you go from in the Fourier domain, you have the data.
Yeah.
It's not the image. But you just take the Fourier transformation and then you go and make the image just by taking Fourier
Yeah.
transformation and just like and then you know clean.
Mhm.
But in terms of doing it in like RML imaging, like or a Bayesian approach, what we do is we do the opposite. We start from some initial image, okay, take a Fourier transformation of that image, and then we do the minimization until we find a good image.
Yeah, yeah.
Okay.
So this was clear, this was clear.
Okay.
So all the different like algorithm, I guess, that you were showing are different ways of doing that, right? Or like.
Yeah, so like in RML, if you see EHT and Smiley, they are more or less doing the same thing as I explained, like as a general method.
I
In
see.
Bayesian approach, when I said there is chemist and comrade, they have their own differences, but again, it's more or less just a Bayesian approach of doing it.
I see.
Yes.
Yeah, this is very powerful because with the variation, you actually explore everything and you get an estimation of the errors. So this is absolutely fantastic, but it's also very time consuming. Usually you don't, I mean, if you're working with clean, I mean, we don't use this because usually with, you know, BLA data or the things like this, I mean, you have a lot of antennas, so you don't have any kind of these issues that we have with the EHT. And then you just do a pre-transformation of the image and of the visibility, you get the image. And with that kind of that amount of data, for instance, if you want to use one of the variation methods, it could take you 1 week to get one image. So it's really overkill because you can imagine. I mean, with variation method, with what Rohan has been doing, you explore every single image that you could have. So you explore before just to make a a final image of just the median of the posterior. You explore every possible image that is consistent with your data. So this is really overkilling. I mean, after this, I mean, what you get is what it is.
I do want to add one thing though. So if Themis takes about 1 week to make an image, Comrade can do that in just few hours.
Just saying.
There is a question in Zoom. So Almudena Prieto, please.
Yes.
Almudena, open your micro and make your question.
Nice to hear from you, Almudena.
You are muted.
Stop sharing, I guess.
No, Almudena, you are muted.
Almudena, can you hear us? I think you are muted.
Maybe it can be typed in the chat.
If you can hear us, Almudena, you can type perhaps. Yes.
No.
Can you write
No.
your?
Okay.
No, that's you. Yes. Okay.
I'm still muted.
Okay, meanwhile, if any other question here in the room? None here?
Oh, the website work.
Okay.
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 That's it.
All right. So then, thank you very much. And you know where we are. So if you have any further questions, just grab one of these guys and overlap and kill them with questions. All right. Thanks a lot.